Welcome to the channel. In this video, before I go on, I want to be clear about sources. Quantum tunneling is a standard prediction of quantum mechanics, and the pilot wave picture I'm using here comes from David Bohm's interpretation of the Schrödinger equation. Nothing in this video proposes new physics. What I'm exploring is whether a persistence-based framing helps connect ideas that already exist across different scales. I want to explore a familiar quantum phenomenon, quantum tunneling, but from a perspective that's quieter and less mystical than it's often presented. Tunneling is usually described as particles doing the impossible, slipping through barriers they don't have enough energy to cross. That description isn't wrong, but it subtly frames tunneling as a violation, as if nature is breaking its own rules. Today, I want to approach it differently. Using David Bohm's pilot wave interpretation, I want to ask whether tunneling is really about particles breaking rules at all, or whether it's about persistent structures shaping what futures remain available. This isn't about proposing new physics. It's about seeing whether a structural framing helps us understand what the existing physics is already saying. Let's begin with the classical picture. Imagine a particle moving toward a barrier that is higher than the particle's energy. In classical physics, the outcome is simple and absolute. The particle reaches the barrier, stops, and turns around. Energy conservation forbids any other result. There is no ambiguity, no probability, no partial crossing. Either the particle has enough energy or it doesn't. This framework works extraordinarily well for everyday objects and for much of engineering, but it begins to fail when we look closely at the microscopic world. In quantum mechanics, particles are not described solely as points following definite trajectories. They are described by wave functions, which spread out in space and evolve over time. When a quantum wave approaches a barrier, something unexpected happens. The wave does not abruptly stop at the barrier. Instead, it partially penetrates it. Beyond the barrier, the wave's amplitude is smaller, but it is not zero. Because measurement outcomes are tied to the square of the wave's amplitude, this means there is a finite probability that the particle will be detected on the far side of the barrier. This is quantum tunneling. The mathematics predicts it precisely, and experiments confirm it over and over again. In the standard or Copenhagen-styled interpretation of quantum mechanics, this is usually where the story ends. The wave function evolves, probabilities are calculated, and when a measurement occurs, the particle is found either reflected or transmitted. Asking what the particle was really doing in between is often treated as either meaningless or unnecessary. The math works, and that's enough. David Bohm proposed a different way of reading the same mathematics. In Bohm's pilot wave theory, the wave function is still real, but the particle is also always real and always has a definite position. The particle does not smear out or exist in multiple places at once. Instead, it moves along a specific trajectory guided by the structure of the wave. The wave evolves according to the usual Schrödinger equation, and the particle's motion is determined by the wave's geometry, particularly its phase structure. The key point is that the wave is global. It extends across the entire experimental setup, including regions the particle has not yet reached. When a wave packet encounters a barrier in Bohm's picture, the wave deforms and reorganizes itself around that barrier. This deformation creates what Bohm called the quantum potential, not an extra source of energy, but a way of rewriting how the wave's structure influences motion. The particle responds to this structure. Some trajectories are guided back, resulting in reflection. Other trajectories are guided forward, passing through the barrier. Which outcome occurs depends on the particle's initial position within the wave packet. Because we do not know that position exactly, the outcomes appear probabilistic, even though the underlying dynamics are deterministic. What's important here is that the particle is not borrowing energy, cheating conservation laws, or performing a miraculous jump. The barrier is not overcome by force. Instead, the global structure of the wave reshapes the effective landscape the particle moves through. The wave persists across the barrier, even where the classical rules would say nothing should happen. That persistence matters. This is where the idea of structure and persistence becomes useful. In tunneling, what enables passage is not the particle alone. It is the continued existence of a coherent structure that spans regions the particle cannot classically access. The wave carries phase relationships, boundary conditions, and correlations that encode information about the entire system. That information constrains what paths remain viable. In that sense, tunneling is not a violation of classical rules so much as a reminder that classical rules are local approximations applied to systems whose true behavior is shaped by global structure. You can think of it this way. Classical physics asks what happens next based only on local conditions. Quantum mechanics, especially in Bohm's framing, asks what futures remain consistent with the full structure of the system. The particle follows one of those futures. The wave is not pushing the particle through the barrier like a force. It is reshaping the space of allowed trajectories. The difference is subtle but profound. This also clarifies why tunneling disappears when coherence is lost. If the wave's structure is disrupted by environmental interaction, what we call decoherence, the persistent correlations that guide trajectories no longer exist. The barrier becomes classically opaque again, not because energy conservation has changed, but because the structure that made tunneling possible has been erased. Persistence, in this context, is fragile. It depends on coherence. Seen this way, tunneling fits naturally into a broader pattern we see across physics. Systems do not remember the past because energy is conserved. Energy can be conserved while all structure is lost. What persists and what acts like memory are constraints, correlations, and large-scale patterns that resist being scrambled. In quantum tunneling, the wave function structure is such a constraint. It carries forward information about the system's configuration and allows outcomes that would otherwise be forbidden. It's important to be clear about what this framing does and does not claim. It does not predict new tunneling rates. It does not modify quantum mechanics. It does not introduce hidden energy sources. It is an interpretive lens, not a competing theory, but it shifts emphasis. Instead of focusing on particles violating rules, it focuses on structures persisting long enough to shape outcomes. That shift matters because the same idea appears again and again in physics. In cosmology, large-scale structures persist long after local conditions have changed. In black hole physics, horizons act as durable records of collapse, even as interior details become inaccessible. In thermodynamics, constraints slow the erasure of information and create long-lived patterns. Quantum tunneling may be one of the smallest scale examples of the same principle, global structure constraining local motion. So the question I want to leave you with is not whether Bohm's interpretation is right or wrong. Experimentally, it makes the same predictions as standard quantum mechanics. The question is whether thinking in terms of persistence and structure helps us see connections we might otherwise miss. Is tunneling an isolated quantum oddity, or is it one expression of a more general rule, that what persists, even quietly, can shape what remains possible? My name is Charles Carroll, and thank you for listening and thinking this through with me. If you have questions, alternative ways of seeing this, or disagreements, I'd genuinely like to hear them in the comments.